It's good morning. It's nice to see you all, and it's nice to be here. And I've actually had 4 lessons in Dutch, and I wanted to say something in Dutch, but decided not to torment English speakers and first of all Dutch speakers. But anyway, my name is Michail. We are going to talk today about exceptions and error handling. And while we are at Java conference and talking about Kotlin, my first question to you is how many of you regularly write code in Java? Please raise your hand. Nice. And how many of you regularly write code in Kotlin? Good. So it's half to half. It's really nice. Let's start. So just to show you what are rich errors. Rich errors, it's a new language feature that we are developing today in Kotlin. And it's a mechanism to handle recoverable errors with this pipe syntax where you can declare some type or an error object and then combine it with different methods and then handle the error at the call site. But it's a teaser. So we'll start with exceptions in Java and Kotlin, pros and cons. We'll check what's this errors as values concept. And then we talk about rich error syntax, semantics, and how we do shortcuts and chain calls. And because we are going to talk about error model, I find these 2 questions helpful, that they can help us to focus on the topic. Because every time you come to a new ecosystem on our language and you want to understand how it works, how to work with errors, it's 2 questions that you typically ask yourself. It's how can I, as a developer, can express that a method might fail, and then if a method actually fails, how can I can handle errors? And if you think about these 2 questions in Java ecosystem, then probably the first thing that will come to our mind is exceptions. But before exceptions, I would like to talk about C. It's the thing that predates exceptions, and why exceptions actually appeared in the language, in the Java language in the first place. And in C, the situation is very simple. We use error codes, we use some global variables, we use signals like null or ferror or something else. And the thing is, while it's very simple, it works everywhere, you actually don't have any type safety. You just return some code, whether it's an int or string or something else. The compiler doesn't force us to check this, and it's very easy to forget this check and then fail the program with some horrendous error, as it typically happens in native. And also, there is no actual ergonomics for nested function calls. So we can write a bunch of code and then handle errors and exceptions somewhat in a centralized way. And Java set a noble goal, actually, to fix this problem. And that's how checked exceptions appeared. And it was really nice way to work with that in the first place. Because now we had checked exceptions. The compiler forced us to check exceptions at the call side. We could write a bunch of code, and then in one single block of catch, we could handle exceptions. And it was nice for a while, because the design of exceptions was not that great. It was easy to misuse checked exceptions and unchecked exceptions because they use the same mechanism. And people tend to throw a lot of exceptions, and at some point you have this problem with exception tunneling when you just have to rethrow either 10 exceptions or just do nothing. And at some point, it became really a problem with boilerplate code, because often you couldn't do anything meaningful in the catch block. And sometimes, people just throw an exception, and the only thing that you could do is just rethrow it. But again, it's more or less fine, because it's a clear way out. You could just rethrow an exception. If you don't know what to do, just rethrow. Maybe you have to update your callers, and at some top-level API boundary, you can handle all your exceptions. And the real problem came to Java 8 is with lambdas, Because with lambdas, you cannot have this escape patch where you can just rethrow an exception. The compiler actually forces you to handle the exception exactly in this lambda. And because the reason that this lambda can be executed somewhere, and you can't just propagate the error to your usage call, because it could be, the lambda could be stored, and then when it's actually invoked, then its stack trace is different. So you actually have to put your try-catch block inside that lambda. There's no way out. And you have to do something like this. And when you force people to write an explicit try-catch block or write some block in somewhere, programmers can be very creative, because it's like, the compiler forced me, I wanted to write some business logic, but now I have to write some meaningful code in catch block. And that's actually a problem, especially maybe mostly for beginners. But if you check even like how people write just this try-catch exception E at GitHub, you find around maybe 10 million files, which means that Java is a very popular language. And also you'll check how people actually handle exceptions. And I'm not saying that's wrong, it's just in a very different manner. Some people just swallow exceptions, some they return null, print stack trace, print some string, and that's for exceptions, for checked exception. If you also check the same for throwable, you'll see the same picture. While with throwables, it's actually way worse, because you actually can catch null pointer exceptions, class cast exceptions, and swallow bugs, issues, and probably it's a problem. And it's not that people write bad code. I also checked our IntelliJ repository and decided not to include it here, because I found that we had like a few dozens of bugs like this. And because in IntelliJ we also do some processing with some process canceled exception. We throw exceptions to check that, to cancel some processes. And of course, at some API boundaries, someone swallowed this exception, and now we have a bug in IntelliJ IDEA. So again, if there is one thing that you can learn from today's presentation, and you have this situation in your code, and you're really unsure what to do, what to write in your catch block, then just rethrow it with an unchecked exception. That will be absolutely fine. Which leads us to the next topic, so that we have checked exceptions, and of course, it means that we have unchecked ones. And unchecked exceptions is that those ones that are not required to be declared or caught, so the compiler won't force you to do anything with this exception at the call side. And initially, the idea was to use these kind of exceptions for unrecoverable errors, like null pointer exceptions, class cast exceptions, array, index out of bound exception, and so on. But also, after years, it became really clear that unchecked exceptions are really helpful for another case, and it's just when you want to handle some piece of code non-locally. So you don't want to handle it just at the caller side, but you want to delegate some execution maybe to another component, maybe to another service, something maybe to framework, and so on. So it's really convenient when you want to signal to your different component and do something across different parts of the code. And often this is the case for frameworks like Spring, for IntelliJ IDEA, because IntelliJ IDEA, if you have a plugin, so you have some extensibility in your system, and you have a plugin, and the plugin throws an exception, you actually don't want to crash the whole IntelliJ IDEA. IntelliJ IDEA has its own mechanism how to deal with exceptions. It will report to user, do some logging, and then that plugin authors can do something meaningful about this. And the same about, for instance, Spring, and even more. So a typical code in Spring when you can use exceptions is to declare your custom exception, which is actually an unchecked one, and then when you do some get a user, try to map it to some DTO, and if it's unsuccessful, then you throw that exception, user not found exception. And it won't actually crash any application. Actually, Spring Framework will catch this exception, check that it actually has this annotation response status, and then it will show you the pretty page and everything will be fine. And that's actually very, very convenient, because at this point, you can change the method, you can change the logic, you don't have to change the callers, as it was with checked exceptions. And yeah, and you also don't have to, you can easily communicate this to Spring. Sometimes if you want to do a custom handler, you can provide an additional method that will be called when the exception is actually caught by the framework. So nice. And yeah, we don't have to handle this exception at call side, which is great. The throwing exception don't force you to change the callers. But it also means that exceptions here, do not act as any part of error model, because if you remember those two questions, like when I come to some ecosystem, like I want to understand how I can specify that my method might fail. And here, actually, the method, it doesn't fail. It uses a different thing of exceptions, and which is to return a new value from your function and to bypass the normal execution of your path. So because here we don't have any signals about potential throws, and actually in your application code, you won't write any try-catch blocks. This is written already in Spring, and you normally shouldn't do that. And if you actually do this, then again, you potentially can swallow this exception, and the pretty page won't be shown to a user. So here, the primary goal of exceptions is to bypass the normal execution path. It's not part of error model. It just appeared that it's very convenient to use this like after a while, not when the Java was designed. Good. And let's check, so in Java and the JVM ecosystem, we have checked exceptions and unchecked ones. And let's check what's going on in other ecosystems. If we check Go, then, which is also very popular for server-side development, then they say that errors are values. If you check Swift, then they have these errors are also values that representative types that conform to error protocol. If you check Rust, then Rust tells you that Rust doesn't have exceptions. Instead, there's a result and panic for unrecoverable errors. If you check hyper-modern programming languages like Zig or Glim, then they also state that they don't have exceptions, they use values instead. So this brings us to the next concept, which is called errors as values. And here it also lies from the fact that exceptions are sequential in their nature. Again, they were designed many years ago when programs were mostly sequential. And if you get an error, then it makes sense to return from a call, propagate it to the caller, and do something about this. And this pattern is encoded by hidden control flow. So we do not use return, we actually use throw, we check, and if they throw an exception, then nobody knows where the execution will continue. And that's why it's hidden. While if you treat errors as values, and we know that values can be programmed, and since errors are values, then it also means that errors can be also programmed. And why it's become more important in nowadays world. First of all, because now we have a lot of asynchronous tasks, and sometimes we start a bunch of threads, virtual threads, just tasks, and if some of them actually failed, we do not want to fail all of them and propagate to the caller. We want to actually wait for all results sometimes, and then reach the consensus whether we want to continue, just take the successful ones, restart the unsuccessful ones, or it's enough and we actually take one of the results. Similar, but slightly different, it's just when we want to manipulate a bulk of failures. If I want to read a bunch of files, I can start reading it in a functional style with some map, and I do not want to fail all of the readings. I want to, again, collect all the results, maybe combine them, and do something about the result. And that's also easier to me when error is just a value. It's not propagated to the caller. And because it's, again, we can program errors, we can do some strategies like repeat, retry, we can do some consensus strategies. And that's of course, it's possible to do in exceptions, and this is what Spring Framework, again, does. But good luck implementing this if you're not in Spring. It can be quite tricky. And again, if someone swallows your exception, then you cannot do anything meaningful about that. And that's, in my opinion, why errors as values becomes more and more important, and one of the central things when you want to work with errors in languages. And also, why, in my opinion, checked exceptions got all these problems is that it was really unclear when an exception is actually checked and when it's unchecked. If you check even like documentation of the throwable and error exception, it's quite misleading, because if you inherit from an exception, then it's checked exception. But exception by itself is it's a child from a throwable. And if you inherit from throwable, then you get an unchecked exception. And I can imagine that some people, and myself included, made a few mistakes when they wanted to do some unchecked exception, but they end up with a checked exception, because while it's the same hierarchy of exceptions, it really depends how you design all of that. And error values and then exceptions or panic or something else, it brings you a clear separation between recoverable errors, so errors that you want to process locally, and actually problems, exceptions like null pointer exception, plus cast exception, and so on. So actually, which are mostly bugs in your system. And now Kotlin. So when we were designing Kotlin, we knew about this problem with exception in Java, because it's also Kotlin had lambdas from day one, and we understood this problem with exceptions, the checked exceptions. They are not really composable with lambdas, so we dropped the concept of checked exceptions, and now we have only unchecked ones. And mostly, we use them for recoverable situations, fail-first behavior, Spring-like cases, and so on. But we also, for today's topic, it's important that we don't have any proper this mechanism with errors as values support. And it's led to various organic approaches to error handling in Kotlin that I would love to show to you in the next slides. And next, we are going to use this simple toy example. I have two methods. It's the first one is just fetch user. It returns nullable JSON. It uses this question mark. Well, right now it's only in Kotlin, but maybe someday Java will also get the syntax with nullables, and I assume that the very same pattern will be used there in Java as well. And we also have function parse user, which declares on JSON and returns a user. And also null here indicates whether it's a network error in case of fetch user, and whether it's a parsing error in case of parse user. So what we can do next? Of course, we can just combine these two methods and write a method getUser when we invoke first fetch user and then parse user. And here it's convenient because we can use safe call operator. We can safely combine a bunch of things. We don't have to do this as in Go, when you just invoke a method, or in C, and then check for error, then do the second call and check for error. Here we can just combine two methods. Then you can invoke, of course, this method getUser, try to get something from a user, and here the compiler will will tell us that you actually have to check for nulls, because it's unsafe to do a direct call. And when we check for null, we actually can safely get properties of the user object. So we have ergonomics for chain calls. It's cool. We have type safety, and we also have this smart cast that we have this flow typing that when you check for null, then you can just invoke the name. But we actually also get a problem, because it's unclear whether it's when we combine these two methods, it's not really clear whether it's a parsing or network error. And if you want to add more errors to our API, then null will combine all of these errors together, and it will be hard then to debug these problems, understand what's actually going on when I actually expected the user to appear. And this is where the next approach comes to play, which is about seal hierarchies. So, okay, nulls, we can leave these methods as they were, but we also introduce a sealed hierarchy of a result where we can say that it's actually a successful result, or it's a network error, or a parsing error. And then we leave our original methods as they were, but now our function getUserSealed, it now returns specific computation result, whether it was a network error, whether it was a parsing error, or it was success. And now that at call side, actually, when we get our result, we can use like a when and go through these successful or error branches and get all the information we need. So we actually get clear errors. It's nice. But also, it's the problem is that here we detached our original methods from result computation. So extensibility is not the best part, because if I would love to change then my fetch user, will have to change all these user result combinations and somehow update the callers. Of course, I lost this thing that now I cannot do chain calls, so I have some verbosity additional. And also we get nesting, which is sometimes fine, but sometimes can lead to unpredictable complexity. So yeah, and also you have to write this user shield all the time, which is, again, quite verbose. And it didn't take as long. Yes, if you do write this all the time, this result shield all the time, maybe you can do a generic version. And this is what a lot of programming languages do, especially in functional programming languages. We just introduce an abstraction that knows about the computation result. It has successful branch and a failure. So what happens with our result? We have fun fetch user result that now returns not a JSON, but a result of JSON. And our parse user result now returns not a user, but a result of user. And then our get user result now also have this, uses some operator, get or else, returns failure if it's a problem, and success if it's okay. And our get user result now has these two branches on success. It's nice. On failure, we have a bunch of errors that we can handle. And we get extensibility. And also what is nice here is that this result is typically common across your framework, across your code. You use the same thing, so methods can communicate with each other. Good. But of course, we get a lot of verbosity. Now we have these get or else things. We have functional operators. We also don't have an exhaustive when, because this error is just throwable. And also, in my opinion, it all could work, and it actually works, because a lot of people use this. But in my opinion, this is a really nice example of accidental complexity. Because if you remember, our piece of code was like this. We used to call only 3 functions. It's fetch user, parse user, and get user. That's basically our business logic here. But when we use some monads like results, something else, try, or either, then the complexity becomes way, way higher. While essential complexity of this piece of code is very simple, but accidental one is very high. And that's, of course, in my opinion, it's a real problem, because when you use nulls and then you want to make your application safer, you have to sacrifice with a lot of complexity and write a lot of code and then maintain it, and of course do bugs and then catch them. And that's why a lot of stuff it was beginning about this thing, why we are working on trying to work on a new thing that we call rich errors. And why we try to improve this error handling mechanism in Kotlin. So it's work in progress, we published the first KEEP with the preliminary design in our Kotlin KEEP repository. You can check it. And next, I'm going to describe its design and design principles. So, rich errors. First of all, we have classes in Kotlin, of course, and now we are going to introduce new modifier error, and it's possible to declare an error class, for instance, network error or parsing error. So it's a new kind of classifiers. Next, we want to now write our functions in the following way. So it returns JSON or network error, like user or parsing error, and now our function getUser now returns user or these two errors. And in order to just write shorter, we can use a type alias to say that it's a user error, which is like network error or parsing error. And our function getUser now returns user or user error. And what happens at the call side? So our function getUser, it's again, we can invoke just fetch user and then parse user using this save call operator, which actually will combine all the errors from these two functions into the user error. At the call side, when we get the getUser, the compiler also prevents us. We cannot call just .name. It's prohibited because it's unsafe. We actually have to check that whether if it's not user, we just say that it's a problem and then return, and then we have the smart cast now to that user is actually user in the else branch, and then we can access the name. So what we want to, again, to achieve here is that it's actually, we have ergonomics for chain calls, we get type safety as with nullable types, and we have conciseness. We actually do not have any nesting, because nesting is inevitable when you have use a wrapper like result or try, and here we'll talk about this why we don't have this one, because I'll talk about this in a few slides. And of course, we did all of that for extensibility because we wanted to avoid this problem when null combines a bunch of errors. And here, because our getUser returns user or a bunch of errors, now we also have all the information about errors, and this one is exhaustive, so that we checked all the errors in the when branch. And that's like a top-level design, so that we are going to dive into it and unpack what's going on there. And first of all, probably you might think that it's actually union types because they look like union types, they act like union types, and they're almost a union types. But actually in the design, it's important that we always have this main actor user and a bunch of attributes, which are like error attributes. And this allows us to do less nesting because we always actually work, as with nullable types, we have like string question mark. We always know that the main thing here is string, and question mark, it helps it to like signal that it might be nullable. But we work with like a string. We can see methods from it, we can work with it, and so on. And here the main limitation is that we can have one main actor, so for instance, some class user, string, int, and several errors. So we actually cannot have int or string, and so on. And that's good for several reasons. And one of them is that it's just easier to reason about, and it's easier for tooling, because if you have always this main actor, then you can inspect, for instance, objects, auto-completion works in your IDE, and so on. Good. So they behave as union types in a sense that you can actually pass, for instance, a user where you expect user or network error, but it's always so-called disjoint union with the main actor of a regular class. Good. So design principles. The first design principle is that errors, they work as values. And we do not have any special rules for control flow. So if you want to return an error, then we simply return a new instance of an error. So we do not have anything like throw, because again, if you throw an exception, then nobody can tell you where the program continues to execute. Because maybe it will be caught, maybe not, maybe it will crash the whole system. It's not clear. the next thing is that we really want to design these errors for recoverable cases. And an instance of an unrecoverable case, it's when you use something like require, or which is actually extension to the type system. Because, for instance, when we have this fun process and we do a bunch of require or asserts, it's like it's this ad hoc type system extensions, because in some ideal world, we could say that this is like non-blank string that contains letter as the first character. And sometimes it's just easier to use ad hoc type extensions. And this is where I think exceptions were great, and we do not want to cover these cases with errors as well. Next, we believe that exhaustiveness is crucial, because if you do this for type safety, then we actually want to be able to process all the potential errors. And so no throwables that can contain all the possible exceptions in your world, including null pointer exceptions, checked exceptions, everything. Now we want to be more precise at this point. And of course, we find it crucial that we want to have chain calls and shortcuts when working with errors. Because I think this matters, because again, if you force people to do tedious checks, then at some point there will be some form of tunneling when people just write this to say that, please, the compiler, let me write my code, I know what I'm doing. And if you want to do this, and if you want to actually to have shortcuts, then we'll provide this, and at least it will be reasonable, maybe not very correct, but actually reasonable way to avoid the problem when you don't want to handle all the errors precisely. So we would love to be able to combine calls in a chain call. So fetch user question mark dot parse, and we want to be able to say that, okay, I'm done with error handling. I'm ready to just throw it in a way like in an unchecked exception. And last but not least, but we want to keep our type system sane and polynomial. So it's about the design with main actor, how these union types will behave at the compile time. Good. So now we have this concept of errors as values, and we see that many languages like moving into that direction. And we can check now that we are familiar with it, what's going on in languages more specifically. So in languages that have more structural typing and less types in their type system, like Go, Lua, Julia, JavaScript, they typically use this pattern with two-value returns. So they have errors as values, but they just return a tuple, where just one is the actual result, and the second one is an error. In programming languages where types are all around, typical uses of result, for instance in Rust, plus some shortcuts in the form of question mark, where you can just invoke a method, put the question mark, which means that if it's an error, then it will be propagated to the caller automatically without changing your signature. In Swift, it's quite similar with more shortcuts. While it has throws, it's actually just a syntactic sugar over result. And in Zig programming language, it's they have very similar to things that we want to have, which is they call error union types. So you can add a bunch of errors. They have quite unusual semantics, so they put errors first. Then they have, instead of pipe, I don't know why, they use an exclamation mark and then the actual type. But they have the same thing. So we have a bunch of errors, then exclamation mark, and the actual main actor. Good. So next thing. So we want to introduce new kind of classifiers. These are just regular classes which are slightly restricted as opposed to regular ones, which means that you can work with them as with classes, as with objects. If you want to carry some data with your errors, for instance, you want to specify that parsing error happened at this position with this problem, then it's just as easy as use a regular class. And this is where it's also, as I mentioned it, in Zig, the error mechanism is very similar to what we want. it's not that similar, because in a way that they actually cannot carry additional data with errors. And it's like one of the, I think, the most prioritized thing in their bug tracker. But unfortunately, it was closed as not planned, because they also want performance, and they compile their attributes in a specific manner so that it doesn't cost any, like it costs less at runtime. But it's a clear way that people would love to carry additional data with errors. So these are regular restricted classes, and they are restricted in a way that error classes can be only final, so you cannot extend from an error class. And also, you cannot have generics. So it's not possible to define an error class which has a generic type parameter t. And one of the questions is that if they are final, then how can I write, for instance, my hierarchies? And the answer is that we would love to use just the type alias and leave the type hierarchy flat. So if previously you had something like that, which you have like fetching result with a successful branch, and then you had a bunch of errors. So if you break down, first of all, success, that data class success is completely useless here, because it just holds a piece of data that is generic. So it's just a wrapper. It doesn't bring, again, anything meaningful here. So first of all, we just remove this. Now we have just main actor. Just if you want to use if you want to work with strings, work with strings. Don't work with success of strings, which is useless. And for errors, we just create a bunch of error classifiers. And to combine all of them, we can use just type alias. And then we can write our fetch data, which is, for instance, returns some useful data or fetching error. Good. Next thing, while these are new kind of error classifiers, also one of the important things is that errors are not subtype of any question mark or Java-lang object. So they actually form a new hierarchy in our type system, which means that if you have an error, then it's not possible to pass it where any is expected type. Or for instance, when you have a generic, you cannot have pass on an error where just t is expected. But you can specify a new bound error, and then everything will work. And this is important for us for type safety, because errors are not regular values in a way that they need a special treatment before using later in your code. The next thing is that we introduced this pipe operator for declaring disjoint union types. So we can declare like int or duplicate ID error or parsing error. We can have just like a bunch of errors, but we cannot have int or strings. And here the thing is that because errors in a separate hierarchy, it's possible to write int or error, because this union is disjoint, so they don't have any common supertype. And because errors are finals, we can use, again, this pipe operator to declare disjoint union, because the type hierarchy is flat, it means that they don't have any intersections, and we can simply have unions of errors. So our updated type hierarchy is going to look like this. So like on the as the root type, we have any or error. Then we have any can be extended from this type. Error can be extended from any or error, and then nothing as the bottom type. Good. And we talked quite a while about the result case, that it's a quite popular thing in languages. The other monad that comes again mostly from functional languages, and like it's a signal when errors as well as concept is becoming more and more popular, is that we also have this optional thing, which is like we have optional T in Java, Swift, we have option in Rust, maybe in Haskell. In Kotlin, we don't have optional because we use just the nullable types for that. And this is where the design with rich errors can be actually simplified, because we with rich errors, we don't have to introduce or use optionals. We can just say that it's T or not found, T or absent, because optional, it's a way to signal that a value might be missing. And while it works, again, because it's a wrapper, you have all the problems with wrappers when you have like list of optionals, like optional of, and then nested options, and then sometimes it's hard to work. And also the other potential problem with optionals and again, all the wrappers is that it's fine to use them on the return type position because you just return an option and then have like some operators like to unpack this option, to map this option to other type. But when you actually have put it in a parameter position, then it's not convenient. You want to signal that this value as a parameter sometimes exists, sometimes not, and you do some logic about this. But if you put it on a parameter position, it means that all callers, even that they have a value, have to wrap it into an option, which is okay, but also already smells and maybe not ideal, which forces you to write overloads and provide two methods, one with option and the other one with a plain value. While here, because it's a union type and you declare, for instance, your parameter type as T or absent, you still can pass just a T without providing conditional overload. Good. Next thing is that, as I mentioned, that we think that shortcuts are important because we want to write business logic. Sometimes we want to combine things. And at the same time, we want to be quite concise and do not lose all the information about the errors. So first thing is that you would love to introduce safe calls. We have this thing for nulls, and it seems to work really nice in Kotlin and makes to have the same for errors. But first of all, how they work, if you have a chain call of expr A ((x per B ((x per C), then we know here that expr A, it has just nullable type A, like expr A ((x per B), it has the type B and question mark, where null can come from expr A or from expr B. And the same for the whole expression. Now it's nullable type C, and null can come from whether it's expr A or expr B or expr C. And now you probably can see the logic, because now if you have this the same for union types, then expr A is just type A or E1. Expr B is type B, where this error can come from expr A, so it's E1 or E2. And the whole thing is just type C or E1 or E2 or E3. And here, again, because we have always only main actor, it's possible to combine these errors together, because it's only one always. We cannot get like type C or type B, and which means that only errors can grow while the main actor remains the same. And it's also convenient because if we think like if you would love to introduce like union types and write just a basic code like this, we have interface in B, it has like foo and bar methods, and have a union type A or B. Then even if I try to invoke something on such A or B, it actually doesn't make any sense, because the only thing that I can invoke there is just some methods from my any, which is like toString equals or hash code. And these, because the common supertype is any. And the same thing actually happens with union types, like with result or either. You cannot invoke anything meaningful on these types like A or B. You can invoke, that's why you have to, of course, learn these operators on success, on failure, like flat map, on result, and so on. While with rich errors, we always know that if you put like a question mark, we can access safely methods from the, for instance, on A or error, we can access methods from A. We can call foo and so on. And from if we have B or error, if you put a question mark, then we can access methods from the interface B. So it, again, and ID will also help you, because if you don't use a safe call operator, it still shows you like auto-completion list, and then the compiler forces you to put something like question mark there or handle your error. The next thing is that the next shortcut that is also helpful and that also often works nice in Kotlin is that we try to be safe, so sometimes we are overly safe and return from methods and mark them as nullables, but we really sure that it's non-nullable. And then we can use like a double exclamation mark to say that if it's actually was nullable, I was wrong, it's fine to throw it with a null pointer exception. And here we want to do the same with rich errors. So if you have actually a like fetch user and it turns out that it returns some error like not found, then this fetch user with 2 exclamation marks will be translated to something fetch user.throw and throw an exception. Because all the errors, they also have this from the basic error class, fun throw, which returns nothing, which means that it actually should throw an exception. And you can override it in case of some user wants to throw exceptions and use exclamation marks. So that's the other thing. Also, the last thing from nullables is that we have also else operator. And this is the thing that where we want to split when we have expr else operator return. We want to get to the right-hand side of the else only if expr is nullable. And it makes a lot of sense to do the same for errors. I have an error, and I do this else operator, and then, for instance, I return from a method or do something else. But here we do not actually want to introduce it for errors because we have a syntactic problem. With nullables, it's very clear that if you get to the right-hand side of your else operator, then it's always nulls. With errors, it's not that clear. It might be some error, it might be a bunch of errors, and there is no place where we can put this information about this expression. Like we cannot extract this like error thing. But good news is that because errors are values, we can program this else operator in a form of helper function. So we actually can define something like method if error, which works on the receiver of values or errors. It gets a lambda that works in case of errors. So we have this e as a parameter in a lambda. And the body of this is just a regular else. Like we check that if this receiver is error, then we invoke the lambda. Otherwise, we return the expression. And now we can do some, because it's an inline function, we can do some non-local returns. For instance, if we get some expression and it turns out that it's an error, then you can simply return from the function if you want to. And if you want to process errors in a more precise way, then you can materialize this error and do a when statement over these errors. Good. The next thing is that, as we discussed, Kotlin doesn't have checked exceptions for a purpose, and primarily use should be for unrecoverable cases and this non-local error handling. But sometimes when we deal with some API that use exceptions, we would love to go from exceptions to errors as values. And here again, because errors are regular values, we can program them and easily transform exceptions into errors. For instance, I can imagine that we add something like that to our standard library where we have like error class throwable error, which handles some exception, and a block that just catches all the exceptions and transform them into like a regular error value. So that, yeah, and of course we will add a version for cancellation exception so that we don't repeat our mistake as we did in the coroutines. And then when we have then some API, like read all lines that can throw like a bunch of IO exceptions, and we don't want to deal with the detection, we want to be like more explicit. Now it's possible to just invoke this run catching as error, which will catch all the exceptions and transform them into our rich error. Good, and As a almost last slide, just want to recap that we designed rich errors to design and handle recoverable error cases and exceptions for everything else. So we want to try to separate this model for recoverable and recoverable situations and make them really distinct in the language. You might have noticed that we try to generalize this nulls as errors pattern because we use ergonomics of safe calls, of exclamation marks. Rich errors, in a way, it's a built-in support for patterns around result or optional. And this thing, of course, is in progress. So we have like a more detailed keep on a repository where you can read more details about our motivation and comment it whether you like or see some problems with that. So we'll answer and we'll have a nice discussion. And that's it. Thanks for your attention. And that's all. Thanks.